we are going to look at what an object's centre of mass is. We're going to look at how to find an object's centre of mass, and we're going to talk about what suspended equilibrium is. Now, you're going to need a few things. A pen and paper would be pretty handy, but if you have a few sheets of paper, that will be very useful for today. If you're feeling especially on the ball, you may also get yourselves some scissors, a bit of string, maybe a lump of blue tack, and even a ruler will probably be quite useful on this one. The ruler you're going to need pretty soon, so if you do have a ruler, go grab it now so that you can use it for the next bit of the lesson. The first question for you is a bit of a recap on last week's stuff. So how does Newton's first law of motion explain what is happening in this GIF that I've got down here for you? So if you want to post your comments, how does Newton's first law of motion explain what is happening in this GIF of the guy in the pink car? Post your comments. Let's see what you think. Doesn't sound particularly scientific, that, Matthew. Let's get a bit of a scientific explanation going. Maybe the thing to do first of all would be to post Newton's first law of motion. What is Newton's first law of motion? Maybe you can think back to last week and you can type out what that is. That might help people out to then see how it might apply to this GIF. Yes, thank you, Karan. So Karan's given us Newton's first law of motion. An object will continue with a constant velocity unless acted on by a force. That is, largely, it will also potentially continue at rest. But yes, continue with a constant velocity unless acted on by a force. That is Newton's first law. So how does Newton's first law apply to this GIF? I haven't got an answer from anybody yet. How can you apply that law to this GIF, to what's happening here? Regis has got the beginnings of a good answer. He said if there's a constant velocity of the toy car sliding down the hill, and then there's a sudden stop when the toy car stops. So we're right. We have this toy car going along with a constant velocity. So have a think about what Newton's first law says. An object with a constant velocity will continue unless acted on by a force. So is there a force acting on the car? If so, what's providing it? No, certainly not gravity. I mean, gravity is involved, but gravity is not the force that's causing the thing that happens at the end of the GIF. It's not friction either. There's very little friction, which is why I think he's unable to stop. What is causing him to stop in this? Yeah, there's a collision. Thank you, Karan. Yeah, so there's a collision, and that collision provides something beginning with F. And there's not friction. 5 letters. Think about Newton's first law. A force. Thank you, Nafi. Very good. So he's moving with a constant velocity until, smack, he hits the side of that thing. A force is applied to him in his toy car, and he's no longer moving with a constant velocity. His motion has been changed. Remember, a force is something which will change the motion of an object. So constant velocity, and then a force is applied, and that changes his motion. It changes his velocity. That's how Newton's first law can explain what's going on here. He moves with a constant velocity until acted on by a force, and that force is provided by the collision of the car with the curb or the bush or whatever it is that he's got there. Yeah. Okay, cool. So let's move onwards then. This is a picture that you may well have seen before. This is something drawn by Leonardo da Vinci, and it's known as Vitruvian Man. Now, the point of Vitruvian Man is to demonstrate that human beings are symmetrical. Human beings are symmetrical, and this is one of the things that Vitruvian Man, this picture by Leonardo da Vinci, is trying to show us. But what does that word symmetrical mean? See if you can post an answer in the comments for me. What does that word symmetrical mean? And if you want to use the internet, if you're not too sure, you have that tool available to you. So why don't you look it up if you're not too sure. What does that word symmetrical mean? Post your answers in the comments for me. The word line, Matthew, may very well be in your answer, but certainly would not be the answer. The word parallel probably wouldn't be in your answer. Ooh, Michelle's got quite an interesting thing there. Michelle says, when you divide an image through the middle and have two identical separate images. Yes, so you may well be dividing it through the middle, but will the images be separate? If you were to divide this man down the middle, would these images be identical? They would be separate, but would they be identical, the images that you produce by dividing them down the middle? Anis has got the word reflected in there. That's definitely going to be part of it. Ishan's got the word mirrored in there, can be mirrored to be identical. I like that. Our robot friend 216391 has joined the fray and says, made up of exactly similar parts facing each other around an axis. I do like that word axis as well. An axis is a line around things, around which things can rotate or be reflected. Ilias says made up of exactly similar parts facing each other or around an axis. Again, that word axis. So I like the words reflection. I like mirrored. I like identical. I like line and axis. Now, the definition that I'm looking for, and this is the one that you should get written down for symmetrical, would be this. When divided down the center, two halves of an object will be identical but mirror images. Now, that line that we've divided down the center, you could call an axis if you wanted to. That's good. I've called it here a line of symmetry. Now, you may well have come across this in maths before, lines of symmetry and symmetrical objects. This is the definition that you're looking for. When divided down the center, two halves of an object will be identical but mirror images. That's what we mean by the word symmetrical. So get that down if you're taking notes. And the line of symmetry on a human being is where I've drawn it here on Vitruvian Man. So straight down from the top of your head down to your feet. That's the direction of the line of symmetry. And around that line, everything on the left and everything on the right are identical, but mirror images of each other, at least outwardly, on a human being. So let's see if we can work out some lines of symmetry. Which of these objects, A to G, are symmetrical, and where would the line of symmetry be? Now, this could be one of those things where you take your piece of paper and your pen, quickly sketch the object down, draw in the line of symmetry, or in some case, lots of lines of symmetry, and maybe take a picture and post it in the comments. You could do something like that. I believe Kieran did a similar kind of thing a few weeks ago. So which ones are symmetrical? Where would the lines of symmetry be? What do you mean by the middle, Anis? Sorry, Jody, what do you mean by the middle there? Jody, you are correct. B is symmetrical. Anis says A, B, and C. Anis is correct. Mohammed Zishan Khan says A, B, and G. You are correct as well. Where are the lines of symmetry, though? Where would they be? Are any of the other ones symmetrical? Good. Anis has given me an answer of where the lines of symmetry would be on shape B and C. She said through the center vertically, which would make good sense. So from the top to the bottom in the center of B, and from the top to the bottom in the center of C. That's good. Milan said F is symmetrical. That's also correct. And F is symmetrical. He says the line would be in that sort of cross bit from the top left down to the bottom right. Milan, you are completely correct. Fantastic. There is in fact another line of symmetry in that object as well, though, in F. 216391 says A, B, C, F, and G. Yes, all 5 of those are symmetrical. Very good. There is another one that's symmetrical as well, though. A could be vertical or horizontal through the center, says Anis. Correct. There are more lines of symmetry in A, though. But Anis, you are correct there. Abigail says D is symmetrical if you cut it vertically. Now, vertically would mean from the top to the bottom, Abigail. So I don't think D is symmetrical if you cut it from the top to the bottom, because that little chunk that's been taken out of the top right corner. D is symmetrical though. So, but how is D symmetrical? Where would you need to draw the line on D to make it symmetrical? Ah, Jack has come in. D, diagonal top right to the bottom left. Very good, Jack. Yes. Good. Okay, cool. So yeah, we got some pretty good ideas on this. Nobody has said E is symmetrical. And that's a good thing because E is definitely not symmetrical. That's the only shape there that isn't. So let me just show you where the lines of symmetry would be on these. So A, as people have mentioned, you can go straight down the middle through the center. You could also go across like that. That would also work. So there's a couple of lines of symmetry on A, but another one, you could go through the diagonal. You could go through the diagonal like that, from the bottom left to the top right, or even from the top left to the bottom right. A, being a rectangular shape, is symmetrical actually in quite a few different ways. You could even draw in a line like this one, and that would give us some. Oh, actually, no. Oh, hang on. I'm being interrupted by my daughter. Just give me 1 second. Yes.
Daddy, I need some paper. So, Mommy.
Okay, it was a request for some paper, and the paper has now been provided. So that is a good thing. So yeah, so we've got on A, we have a whole bunch of lines of symmetry, which is fantastic. We just give me 1 second. I'm just altering something here. Okay, cool. So we've got a whole bunch of lines of symmetry on A. B also has a whole bunch of lines of symmetry. Sorry, B has what? I've been thrown off my game, you see, by my daughter coming in. B from top to bottom, as Anis said. C is also from top to bottom. Only one line of symmetry on B, only one line of symmetry on C. D has a line of symmetry. I think it was Jack that told us this one. Was it Jack? Yeah, Jack says diagonal from top right to bottom left. E doesn't have any lines of symmetry. E is not a symmetrical object. Oh, Karan has come in with, yeah, that's brilliant, Karan. Well done. I think you got most of those, actually. Some of them have got more than one lines of symmetry, but those are pretty good. Well done. F, you can go down there, as Milen told us, but you can also, there's also a line of symmetry this direction. If you were to do the line of symmetry like that, both sides of those would be identical, but mirror images of each other. And G has a line of symmetry that way and also a line of symmetry that way. So objects can have no lines of symmetry at all, like with E. They could have one line of symmetry, like with B or C or D. So D isn't symmetrical diagonally. Yes, it is. Why would you? Oh, Anis. Right, okay. Every so often, a teacher makes a mistake. And I have indeed made a bit of an error with D, and Anis has pointed it out, and I've just seen the error. I've seen the error of my ways. I'm going to alter the image, but I want you to see if you can post in the comments, why is Anis right? Why is D not symmetrical in the way that I have drawn it here? Post in the comments about that. I'm going to alter my image so that you can, so we can see it. Oh, Anis, you horrible, horrible person. You are entirely correct. So the problems with A and D, Anis, maybe you could point out what shape should A and D be if they were going to be symmetrical diagonally like that? Yes, both Karan and Anis are correct. Yeah, absolutely right. Guys, thank you so much, you two. I'm going to alter my diagrams a little bit to make them the correct shapes for this. So those are now squares. A, B, C, and D are now all, sorry, A to D are now squares. So I'm just going to alter where I put my lines just a touch so that this working. Anis, thank you so much. So now we have those lines and they are correct. Good. Okay. And if you'd like to take next week's lesson, that's absolutely perfect. That'd be wonderful. Give me a bit of a break. But yeah, that was fantastic. Well done, Alice. Really, really good spot there. Thank you for pointing that out. So we've got a few symmetrical objects. One asymmetrical object. An object can have one line of symmetry, like with B, C, and D. It can have two lines of symmetry, like with F and G, or it can have multiple lines of symmetry. It can have four. It can have a whole bunch. A circle has basically an infinite number of lines of symmetry, and A has 4 there. Okay, cool. So let's move on. This is where you're going to need your ruler. So hopefully you have a bit of a ruler to hand. I want you to pick it up. That's your first command. Pick up your ruler for me, please. And we're going to use it to try something. First of all, tell me, is your ruler symmetrical or asymmetrical? If it has holes in it, like this one here, you can just ignore those holes, and any writing that's on the ruler as well. But as a shape, is your ruler symmetrical or is it asymmetrical? Now, the 30 centimeter ruler would probably be the best one. Yeah, everyone's going for symmetrical. How many lines of symmetry does this ruler have? Does your ruler have? How many lines of symmetry and where would they be? Alice again proving herself to be the symmetry queen. Coming in there first with the answer. Yeah, there are 2 lines of symmetry. The 2 lines of symmetry are straight across that way and straight down that way. So we can divide it in half and it would provide a mirror image, an identical mirror image in those 2 lines of symmetry. Cool. So what I want you to try and do is try to balance your ruler horizontally on your finger. So I've got a bit of a diagram there. You can see what's going on. I want you to try and balance it on your finger. And I want you to see what you notice about where your finger has to be for the ruler to balance, and post where in terms of centimeters, which are the 0 to 30 on the ruler that I've got there, where in terms of centimeters does your finger have to be to balance? Yeah, and it's again coming in there first. Well done. Yeah, 15 centimeters in the middle. So hopefully you've got a 30 centimeter ruler there. If you have a 15 centimeter ruler, it would probably be at about 7.5 is where your finger would balance. But yeah, 15 centimeters is where it should balance. And if you notice, 15 centimeters is that middle line of symmetry that I've got highlighted there on the ruler. So that middle line of symmetry corresponds to where what we call the center of mass is. And that's what we're going to be talking about today, is center of mass. So a ruler is something we would describe as a uniform object. That word uniform, the uni bit means one, and the form bit means thing, basically. So it's made of one thing. So it's an object made of one thing. And that's because it has its mass completely evenly distributed throughout the ruler. So it's the same thickness and so on, and it's the same density throughout. So we call a ruler a uniform object. It's a term that you need to remember and be aware of. So we get that balancing happening at that central point, 15 centimeters on a 30 centimeter ruler. We would describe a ruler as being a uniform object. Graham, we'll come on to your question again in a little bit. When I've shown some bits about a slide, about swings, Karan, you can ask your question again about standing on one foot, because I think that's probably going to be a better point to ask that question, if that's all right. So the lines of symmetry that we have on a ruler, I have got an extra line of symmetry on there. Let me just get rid of that. So the lines of symmetry we have on a ruler are here, and the center of mass is where those lines cross over. Okay, it's where those lines cross over. So those 2 lines will cross over, that line of symmetry through the center, that line of symmetry at 15 centimeters. is where we would see the center of mass. I'm just reading the comments, and Karan has posted, can someone give me the reasoning to why a ruler is a uniform object? Okay, that's fine. We'll go back and have a quick look at that before we move on to the stuff to do with center of mass. When we talk about a uniform object, Karan, what we are talking about is an object that is made entirely of basically of the same material. So something that's made of the same material to start with, which would then mean that this second point is satisfied. Its density is the same throughout. So if something's made of the same material, its density is going to be the same, and the mass is evenly distributed. Now, when we say the mass is evenly distributed, we don't mean that it's really that the ruler is really thick at one end and really thin at the other, because then the mass would not be evenly distributed. With a ruler has the same thickness throughout. So because it has the same thickness throughout, its mass is evenly distributed throughout it. So it's something that's made of the same material, so it's the same density throughout it. And generally speaking, it will have the same thickness throughout as well. So a piece of paper is a good example of a uniform object as well. And a ruler is a pretty good example too. Okay, cool. So those two lines cross over at the same point. They cross over at the same point there, and that is the point at which we would say that's where the center of mass is. Because a ruler is uniform, that helps. That means that we can then say that the center of mass is through those points. Now we need to have a term, or we need to have a definition even for the term center of mass. Thinking about what we've said, what might the definition be for center of mass? Post your answers in the comments. Let's see what you've got, what we can come up with. Mohammed's got a pretty good answer there. Point through which all the weight seems to act. That's quite good. Anis has gone for the center of mass is the crossover of symmetry and where all the weight is distributed equally around it. I prefer Mohammed Zishan's answer there, I think, Anis. I do like that you've got the crossover of symmetry. That's how we can find the center of mass for a uniform object like a ruler. However, you, me, everyone else who's listening into this, we are not uniform objects. We don't have the same thickness. Our mass is not evenly distributed around us, but we do still have a center of mass. Anyone else got any answers for what a center of mass might be? Okay, we've got a couple. We've got Ilias. The center of mass of a distribution of mass in space is the unique point where the weighted relative position of the distributed mass sums to 0. It is a hypothetical point where entire mass of an object may be assumed to be concentrated to visualize its motion. I'm assuming you've got that from somewhere else, which is great. But that's I think the bit on the end is the bit that's probably the most pertinent to GCSE physics, Ilias. The point where the entire mass of an object may be assumed to be concentrated is probably the bit that we like the most there. Regis has gone for the center of mass is a point where all the weight sums up to 0. We do have something summing up to 0. We have a point, we have a force down on the left hand side, for instance, and force down on the right hand side of, if you think of a seesaw or your ruler balancing on your finger. It's where those two forces downwards would sum up to 0, I suppose that would work. But the definition that we need for GCSE is this: the point where an object's mass can be thought of as being concentrated. That is the definition that we need for GCSE. So center of mass, the point where an object's mass can be thought of as being concentrated. And just an additional thing to that, and some people did actually mention this in the comments, we can think of an object's weight as acting through its center of mass. So your weight, if you recall, is the force that you exert downwards. It's the force that you exert downwards towards the center of the earth. That's what your weight is the force you exert downwards. So an object's center of mass we can think of as being the point through which that weight acts. If I wanted to balance a ruler, for instance, I need to do that at that central point, as we discovered, because the ruler is pressing downwards towards the center of the earth. That's its weight acting downwards. And the reason I need to put my finger there at that central point is that we can imagine that the object's weight is all concentrated, all of its mass is concentrated at that central point, meaning that the weight acts through that central point, through its center of mass. If you have any questions, please do post them. I may tell you to post them later on when we get to a bit that's a bit more relevant, but if you do have any questions, please do post them and I'll do my best to answer them as we go through. So that's what center of mass is. If you've got your notes, make sure you've got that definition down. Right then, so moving onwards. This PowerPoint, by the way, is going to be available in the files section, and I'll be posting a link to the YouTube video as well so that you can look at it later on if there's any bits you missed. So next learning objective is this one, how to find an object's center of mass. So how to find the center of mass of anything is what we're going to be looking at. The best thing, or the thing that we need to do, is to draw two lines through it, generally speaking, two lines of symmetry if it's a nice symmetrical object. More than two lines is generally a good idea. So here are two lines drawn in here. Why might drawing more lines of symmetry be a sensible option? We've drawn two lines in here, we've seen where they cross over, and we've said, well, that's it, that's our center of mass. And that's what we could do with the ruler as well. We draw on those two lines of symmetry. Where they cross over is the center of mass. But why might it be a good idea to draw in a third line? This is a good GCSE practical technique as well. And this is getting in there, accuracy. Josh is also mentioning reliability. Maybe someone can explain what that third result, that third line might tell us. The ideas of accuracy and reliability, though, are certainly pretty good. Anyone else got anything more to add? Yeah, that's good, man. Yeah, it helps you to make sure that it is in fact the center of mass. So if I draw in a third line here, it allows us to spot errors in the same way that we repeat any experiment that we do at GCSE. We repeat it 3 times in order to spot any anomalous results. We could draw in 3 lines on a shape in order to make sure they all cross over. If they don't all cross over, at least one of those lines is probably wrong and it's worth doing it again. So I've drawn in a third line here. Those 3 lines do not cross over. So one of the lines I've drawn in is obviously not correct. Samia has said, what if an object only has one line of symmetry? I'm gonna show you a technique to counter that in a minute, Samia. If an object has more than one line of symmetry, like a circle or a square, then this technique works quite well. If the object, though, as Samia points out, has only one line of symmetry, or indeed no lines of symmetry whatsoever, I'm going to show you a technique so that you can get that sorted out. But we'll just concentrate on these nicely symmetrical objects for the time being, Samia. Stay tuned for how to do it with less symmetrical objects. These particular lines don't meet up, so we've obviously made an error somewhere. We're going to do it again to make sure that it's okay. So we draw in one line, draw in another line, draw in a third line. Oh, phew, these ones now do cross over. So that's better. Sometimes we can't draw more than 2 lines, but if you can, it's worth doing it because the third line helps you sort of check that the work you did on the first 2 was correct. If the work you did on the first 2 was not correct, then the third line won't pass through the center, and you know that you need to do it again. Right. Milan's got a question. Does that mean that the more angles a shape has, the more lines there can be? If we're talking about symmetrical objects, the object that has the most lines of symmetry, Milan, is a circle like this one. But certainly an octagon has more lines of symmetry than a hexagon, for instance. An octagon has 8 corners, a hexagon has 6. So kind of true. Does this mean that the more angles a shape has, the more lines there can be? If it's a nice regular polygon, like a hexagon or an octagon, then yeah, the more angles it has, the more lines of symmetry there can be. But if it's an irregular shape, which we're going to come to in a minute, then the answer is no to that one. We are only dealing, Jack has asked, what if it's not uniform? We're only going to be dealing with uniform objects, and we only need to worry about uniform objects. We may, if we have time towards the end of this, get on and chat about non-uniform objects like a human being or a dog, or I'm just looking around my room, what else? A computer, or I don't know, something like that. Yeah, we can talk about how to find the center of mass of an object like that as well. Kiran's face, he's chimed in there. Yes, we can find the center of mass of Kiran's head. Why not? It will involve chopping it off though, Kiran, to isolate it from the body. Right. Where is the center of mass of these objects? These, I'm telling you, are three uniform objects. They're of the material they're made from is the same density, and they're the same thickness the whole way through. Where would the center of mass of these objects be? Maybe draw the objects. The first and the third would be the easiest ones to draw, and then try it out. Take a picture, post it in the comments. Hannes has pointed out quite correctly that the center of mass for these particular objects will indeed be in the center. It's more about the technique of finding the center of mass, I suppose, with this one. Karan pointing out that donuts have a hole in the center to allow them to cook evenly. Thank you, Karan. It's also because they're Jesus's favorite snack. They are indeed holy. I'm here all week. Okay, cool. So has anybody got, if you are having a go at this on a piece of paper, just quickly just post I am having a go at this or yes or something, so I know that your pictures are imminent. Otherwise I'll show you where the center of mass is on these three objects. Yeah, Milan's telling us the technique that we need to use. Okay, right. I'm gonna show you where the lines would need to be. So circle, we've got our one line across there. We've got another line down there. Always a good idea to draw in a third one as well, just to make sure that you are going in the right direction. And then we have our center of mass there. Good. With this next one, which is a hexagon, it's not a regular hexagon, as in it doesn't have, does not have, what's the word I'm looking for? It's not got the same length sides all the way around. It's not a regular hexagon. This is an irregular hexagon. However, it is still pretty much a regular shape. Now, I'm going to draw in three lines here. I want you to tell me, and Anis is probably going to be the first one to get this right, I imagine. I want you to tell me what is unusual about the three lines that I'm drawing in on this. Let's have a look. Anis, as predicted, was the first one to come in. So the diagonal ones don't actually make it symmetrical. However, those diagonal lines that I've drawn in there, the one from the top left to the bottom right and from the bottom left to the top right, they do divide it down the center quite nicely. And the amount of substance, the amount of the object on each side of the line will be the same on each side of the line. So that does actually still work quite nicely and does line up properly in the center to give us the center of mass. This triangle that I've got down here is an equilateral triangle, so each of the angles are 60 degrees. So this one definitely does work like that. We've got 1, 2, and 3, and the center of mass is there. Now, triangles, when you draw the lines of symmetry on them like this, can often look a little bit like that's not really where the center of the triangle should be. Now, one thing you can do, because it often makes it look like the center is too low. You may well think that the center is too low there. One thing you can do, there are two things you can do, in fact, but the first thing you can do is turn your head on the side. If you turn your head on the side, you should be able to see that it is actually in the center. It will look kind of too low as well if you turn your head to the left or turn your head to the right to make the left side or the right side the bottom. The other thing you can do is you can break out your ruler and you can actually measure them up. So I've done that for you. If we look at it like this, I've got 0 from the bottom left up to 12 up at the top there. And this red line here is coming in at 6, so halfway along that side. Again, down here, it's coming in at 6, and again on this side coming in here at 6. So these are, in fact, dividing the triangles in half perfectly. These are definitely lines of symmetry, and so they do cross over in the center. Why is the bottom ruler wrong? Click around. It's close enough. Karan's saying that it doesn't quite touch 12 on the bottom ruler, and I think that's largely because of the way that I've put together the PowerPoint, but it's basically at 12. You get the idea. Okay, so a piece of paper, like an A4 piece of paper, like this one, is a uniform object. Let's just recap. What is a uniform object? What are the two things that make an object uniform? Post them in the comments. So Milen's saying symmetrical and has a center of mass. Any object with mass, Milen, will have a center of mass, and that's what we're going to be looking at with this next bit. Something that's uniform does not need to be symmetrical. Alyssa says the mass needs to be evenly distributed. That is correct. There is something else though. What's the other thing? So its mass needs to be evenly distributed. And what is the other thing? Farhan coming in. All mass evenly distributed and the density the same throughout. Fantastic. So those are the two things that we need to have for a uniform object. So a piece of A4 paper or a piece of card has all of its mass evenly distributed and its density is the same throughout. So we can describe it as being a uniform object. So you could find its center of mass by drawing at least 2 lines through there. You can draw in a third one. Now Anis is going to tell me, well, that third one is not a line of symmetry, but what is true with this third line, as I'm sure Anis will point out to me as well, is that the amount of paper is the same on each side. Those 2 triangles that it draws are identical, despite not being true lines of symmetry. Karan's asking if we have any more fancy animations today. Are these animations not fancy enough for you, Karan? We do have some animations coming up, so stay tuned. But they're probably not quite as fancy as a ball rolling off a desk like last week, because that was, pretty tip top. But let's see what we've got. So yeah, you draw your lines of symmetry. And if you want to at home, you can give this a go. You can also do this if you can draw them in with a ruler. You can also do it by folding. You can simply fold a piece of paper in half 3 ways. And if you do that, or you can draw it with a pencil if you want to, grab a piece of paper and give this a go. If you do that and you put your finger at that point, at that center of mass on the piece of paper, and then pick the piece of paper up on the end of your finger, what happens? Anis, you are really good with your symmetry, I've got to say. Anis has pointed out if you flipped one side of the symmetry, it would be symmetrical in a kite shape. Yeah, absolutely, it would be. So guys, I want you to give this a go. I want you to get a bit of paper. I want you to fold it in the ways that I've shown you on this diagram. And then I want you to put your finger at the center of mass underneath the piece of paper and lift the piece of paper up and tell me what happens. Ah, Josh, yes, the corners flop down, absolutely. But somebody's just mentioned the word balance. Yeah, Ines. Ines is being very sensible and very on the ball today. I am very impressed by this. But yeah, you should find that the piece of paper will balance. The piece of paper will balance at its center of mass. If you support it at its center of mass, it will balance. It won't fall down. Yeah. Now, we're going to take a piece of paper again, and we're going to cut it up into an irregular shape. So Karan was after an animation. Karan, here is an animation of me chopping up a piece of paper. How about that then? Not quite as smooth as a ball rolling off the table, but we now have a chopped up piece of paper. I've chopped it into a random shape. This is not a shape that represents anything. It's certainly not a symmetrical shape. It is just an irregular shape. Now, our piece of paper is still a uniform object. Its mass is still the same throughout. It's distributed evenly and its density is the same throughout. So this piece of paper, although now cut up into a weird shape, it is still a uniform object, but we can't draw any lines of symmetry on it easily. There you go. Right, so its center of mass is difficult to determine because we can't draw in those lines of symmetry very easily. We're going to need a different method for these irregular, or we could call them asymmetrical. The A bit, when you put an A on the front of a word, it means not, essentially. So you can have something that is moral, or you can have something that is amoral. You can have somebody who believes in God, who would be a theist, or you can have someone who doesn't believe in God, who would be an atheist. So that A on the beginning of a word, like symmetrical and asymmetrical, means either symmetrical or not symmetrical. Immoral and amoral are different things, Josh. So we're going to need a different method for these two things. And if we were to be doing it in the lab, we'd have a setup like this. We get one of those Boston clamp stands. We'd have a little bar coming out across the top. We'd have our funny shaped bit of card. We'd have a bit of string, and on the end of the string, we'd have a little weight, and this is called a plumb line or a plumb bob, which is pretty good. The reason why it's called a plumb line, incidentally, is because the Latin word for lead, as you may well know, is plumbum, which is why the symbol on the periodic table for lead is PB for plumbum. And a plumb line traditionally was made with a bit of lead on the end of it, which is why it ended up being called a plumb line. So Karan's asking, do we have to draw the diagram? Well, yeah, any notes that you want to take, Karan, that may be useful, absolutely. So I'm going to walk you through, because I don't have a Boston clamp and I don't have all these other bits and pieces here. I have instead, mainly for the benefit of Karan and Josh, who seem to enjoy these things, I've put together a bit of a PowerPoint for you to show you how to do it. So you cut out your card. There we are, cutting out the card, and hang it up so that it swings freely. So I've got a drawing pin up at the top there, which is what that little sort of star thing represents. And I've hung my card up so that it can swing freely. If I were to push that from left to right, it would end up resolving back to this position. I then hang up my plumb line. There's my plumb line, which is, as I said, a string with a weight on the end from that same point. So from that point where the card is hanging. And then very carefully, and if you get a chance to do this in the lab, you'll notice it's quite difficult to do. Normally best with a felt tip pen, because you can get a good you can just touch very lightly on the paper and it will leave a mark. Draw down your line, the line that we've got there. So that's our first line. Now what this line is showing us is it's a bit like a line of symmetry. The card on the left is exerting a turning force anti-clockwise, and the card on the right is exerting a turning force clockwise, and those are balanced out. So we have a sort of balanced thing going on here, an equilibrium, which we'll talk about later on this lesson, that's going on here. We hang the card from a different corner and we repeat it a couple of times. So we hang it from this corner, perhaps draw down there, then we might hang it from this corner and draw down there. So we've got our three lines that we've drawn in here, and they all meet in the middle, meaning that we've found the center of mass of this irregular shaped object. Mohammed Zishan Khan has a question: will the center of mass hang below the point of support? An amazingly good question, Mohammed. Yes. So the center of mass will always, for an object that has been suspended, that's been hung up, will always hang down below that point of support. And we're going to be talking more about that towards the end of this lesson. But yeah, absolutely, Mohammed Zishan Khan. In fact, I notice people are giving people likes. I'm going to give you a like because I really do like that. It's a very, very good question. Josh has credited my animation skills once again, so thank you very much for that, Josh. Okay, so let's run through the method just one more time, just to make sure that we know what's going on. We cut out some card, we hang it up so that it swings nice and freely. We hang down our plumb line, which is that string with the weight on the end. Draw a line down. It's best to do that with a felt tip pen because it's you can touch the card or the paper really lightly and still leave a mark. Hang it up from a different corner and repeat the process. Hang up our plumb line, draw in our line. And then, because it's always good to do a third one to make sure we haven't messed it up, hang it up from a third point, draw in the line again. Where those lines meet is our center of mass. And again, if I were to put my finger underneath the card at the center of mass, I should get it to balance nicely on the tip of my finger, because the turning forces in all the directions will balance out and equal 0, meaning that we can think of the mass and the weight of it as all acting through that center of mass. It's a practical. Ishan's asked, is this a practical that we need to know? And the answer, Ishan, is it's certainly worth knowing. I'll show you it in the book. Hopefully you can now see the textbook in here. It's not a required practical, but it is one that is worth knowing about. These textbook pages I'm going to put up in the files section as well, so that you've got them. It's all outlined in here so that you can have a bit of a look at it as well. Okay. Right, Jack, welcome. So the way you can test then that this is definitely the center of mass is by balancing it on the point of your finger. And if you get it to balance on the point of your finger, then yes, it is indeed the center of mass. Okay, cool. Right. Karan's asking about Johnny Long. Oh, right. Oh, I probably had. Did I have him open on my? Yes. Okay. Very good. Johnny Long's a bass player, Karan. Why not have a bit of a look? So the word suspend. The word suspend. What does that word suspend mean? Can we give a bit of a definition? Because it's one of those words that you might not understand. What does the word suspend mean? Write that down for me if you can in the comments. While you're doing that, Milen's asked a question. So do you have any video recommendations for this lesson? Yes, Milen, I indeed do. If you check your Teams and go to your class, your science classes channel, I've posted a couple of videos in there that you should have a bit of a look at to better understand center of mass. Ishan is saying the word suspend means when the mass is not evenly distributed, so the center of mass is below the base of support. It's slightly overcomplicated a little bit. The word suspend basically just means to hang from a point, and but you've got some pretty good stuff in there, Ishan. You're talking about the center of mass being below the place that it's supported. That is definitely what happens. That's what we're going to be talking about right now, which is suspended equilibrium. So we would say that a swing at the park we would describe as being suspended. Right, just 1 second. Okay, cool. So you're at the park, you're sitting on a swing. This is a situation I'm sure you can imagine yourself in. You're at the park, you're sitting yourself on a swing. There's no one else around and your feet don't touch the ground. You're obviously quite young. Maybe you've been left there by accident and you're sitting on the swing and there's nowhere for you to go. You may as well do some swinging. So how could you get that swing swinging? What would you do in order to get the swing swinging? If you were sat on it, there's no one else around to push you, and your feet don't touch the ground, so you can't get someone else to help you, and you can't push yourself off with your feet. Swing your legs, says Anis. Build momentum, says Jack. Probably, yeah, you would be building up a bit of momentum, I suppose, in either direction. Swing your legs is probably the best answer that we've got there from Anis. Yeah, you might swing your legs, or you might, my idea would be to lean backwards and forwards. That's what I tend to do when I'm on the swings, is I lean backwards, and that kind of pushes the swing forwards. I then lean forwards, that pushes the swing backwards. Do that repeatedly, and the swing starts to get going. But why does that work? What are you doing when you lean backwards and forwards, or push your legs out, as Anna said, on the swings? What does that actually do? How does that work? What is it actually doing to you? Think about what we've talked about so far. Yeah, we're creating a force, or we're not. We're shifting something. Mohammed Zishan Khan says we're shifting the center of gravity, or in this case, the center of mass, I think would be the term that we want to go for. Yes, Mohammed Zishan Khan, we are shifting our center of mass. So Mohammed's got the answer there. Shifting our center of mass, changing your suspended equilibrium. Now we're going to need to work out what this term suspended equilibrium means. So let's talk about it. Let's talk about what suspended equilibrium actually means. We've got this word suspend. We know that if something is suspended, we know that it's hanging from something. So let's have a look through this. I've got a bit here to try and work out what suspended equilibrium means. Milan's just asked a question: does changing center of mass create a force? If you change your center of mass, Milan, you are shifting. That's a very good question, actually, Milan. Does changing your center of mass create a force? Well, you are shifting where your center of mass is. You're changing where your body, where the weight of your body is acting downwards from, relative to where the swing has been suspended from. Now this changes the turning forces. This changes the turning forces that are causing the swing to sit still. The swing is sitting still because the turning forces are balanced. You have the same turning force to the left and to the right, or clockwise and anti-clockwise. When you shift your legs or you lean backwards, you're putting more turning force if you lean backwards on that left side, so anti-clockwise, than you are on the right hand side. So you are shifting where the forces are being applied, certainly. Right, so let's have a look at this. When you're sitting still, you're completely sitting still, your weight is acting down through your center of mass, and the turning forces on each side are equal. So the force that would cause you to move in one direction or the other, about that sort of pivot up at the top of the swing, is the same in both directions. And because those forces are the same, the resultant turning force would be 0. So you're not going to move. You only move if you have a resultant force that is greater than 0. When you're leaning back or you swung your legs out, your weight is still acting down through your center of mass, but you've now shifted your center of mass somewhat. So the turning forces are now unequal. So when previously we had the same turning force on the left and the right, and those forces then balanced out, nullified each other to become a resultant force of 0. When you shift your mass, those turning forces become unequal. When you lie back like this, the turning force on that left-hand side, so on the back of this person, is bigger than it is on the front. So you start to move around, in this case, anti-clockwise. The bottom of the swing will move forwards. When you then lean forwards again, the bottom of the swing will move backwards, and that's how you can get yourself starting to move. The swing has to move to adjust to your new center of mass position. Okay, so you've had this fun. You now stop swinging yourself completely. What position will you return to? And what might you be able to say? What term might you be able to use to describe the position that you've now returned to? Jack, I think you're probably better at using a swing than that. Jack said he's going to be on the floor. It's unlikely. Mohammed Zishan Khan says you'd be in a stable position. Very good. Yes, you would be in a stable position. Anna says you'd be back at the beginning point. Very good. Yes, you would be back at the beginning point. What term might we use to describe the situation you're in when you're at that beginning point, where you're in a stable position, in that starting position, as Milan's just said? Clue is written in the learning objective for this part of the lesson. Oh, Mohammed Zishan Khan's got half the answer. Mohammed Zishan Khan says you would return to a point which we would describe as being equilibrium. Oh, La Bella, fantastic. Got in there just before Josh. Suspended equilibrium, yes. So you will return to this central point, to this starting position that you got in there. I'm just going to give La Bella a like on that one. Very good. And we would call that suspended equilibrium. We're now in suspended equilibrium. Our weight is acting down through our center of mass, as it always is. And the turning force is equal again on both sides. We have the same turning force on the left, pushing us around clockwise, pushing us around anti-clockwise, as we do on the right, pushing us around clockwise. So we're now in suspended equilibrium. We need a definition. We need to be able to say what suspended equilibrium is. So what do you reckon? Post in the comments if you could. Can you describe what suspended equilibrium is? Ishan saying a stable center of mass. Yeah, you would certainly have a stable center of mass, but not touching the floor. Absolutely not touching the floor because you are suspended. What are you directly beneath when you're suspended and in stable equilibrium, Ishan? We're not talking about the base here, Mohammed Zishan Khan. We're talking about, because this thing doesn't really have a base as such, we're talking more about the point of suspension, where the swing is attached to the to the swing set. We'd call that the point of suspension. So Mohammed Zishan Khan, I wonder if you can change that sentence where you said the center of mass must be above the base. We want to talk instead about it being below something else. Okay, right, we're not getting many more answers, so let's have a look. Can you describe what suspended equilibrium is? Well, it's when the object is at rest with its center of mass directly below the point of suspension. Now, points of suspension, when we're talking about the point of suspension on something that's been suspended, something that's been hung up, we talk about where it's attached. So on a swing, that would be where the swing is attached to the top of the swing set. If you had, say, a flower basket outside a pub or something like that, it's where that basket has been hung up. So that's the first bit. So we would say that an object is in suspended equilibrium if it has the same amount of turning force on either side. Now, the turning force is the force that's going to cause something to turn. That's essentially what we're talking about there. A force down on the right-hand side of this person where his legs are, if you were to push that guy's legs downwards, he would start to turn, if you look at this, in a clockwise fashion. Push his legs, the guy is going to turn in a clockwise fashion. So there's a turning force in what we would say a clockwise turning force on the guy's legs side. On his head and his body side there is a turning force that is anti-clockwise. If you were to push the side where his head and his body is, the guy would move to the right. So he would move an anti-clockwise way around that point of suspension. Now, when something is in suspended equilibrium, those turning forces, that force that's pushing it left and that force that's pushing it right, are balanced. They are in equilibrium. They are the same. They add up to 0. We would say that the resultant turning force is 0. Guys, I told you at the start of the lesson that if you would like to use Google to get your answers to help you understand things better, that I heartily encourage you doing that. The best thing that you can do to push your knowledge and understanding of the world around you forward is to look up stuff that you don't know. So absolutely 100%, I want you to be Googling these things. I want you to be looking up these answers and doing your best to understand them. So when people in the comment section are getting some answers from the internet, they are working hard to understand what is going on, and I applaud them for that. So please do carry on. Jack, if we have anything like that, I'm just going to boot you out. I'm just going to get you out of this so that you can't post things like that. Okay, right. So the textbook pages, I can't remember whether I've put them up yet, but I certainly will be up in the next few minutes on the files section of the Year 10 General Chat. So I'll make sure those are there for you. You need to log into Seneca. Your teacher probably would have done it by now, but if not, we'll be doing it over the next 24 hours. We'll be setting you some sections on Seneca to have a look at to do with forces. And you need to get those done for Friday, will be the deadline for that. I've also posted on your classes channel threads, I've posted some videos that would be useful to watch about centre of mass. You've got the PowerPoints available to you as well. I've linked to those in your classes channels on Teams. So you can look back through those. This lesson will be uploaded to YouTube because it will allow people to view it. We've had about 40 or 45 people in this today, so there's a lot of people who would need to have a look at this. So that'll be going on to the SRS Science YouTube channel, which you can like and subscribe to. I've always wanted to say like and subscribe in a video. I'm getting to say it now. Like and subscribe to our channel. Why not? And then you can see anything that you might have missed or just go back through it as well. The channel name is SRS Science. So SRS for Sydney Russell School. Sydney Russell School Science, SRS Science. There's only a few videos up there so far because we only started doing this towards the end of last week, but hopefully it will turn out to be quite a useful resource for you. Josh has said, yeah, like, comment and subscribe with notifications on. Absolutely, that's what we want you to do. That's about it though. So that's centre of mass. That's what you need to know. The stuff to do with suspended equilibrium, probably the trickiest part of this. I'll be hanging around for 10 or 15 minutes to take any questions that you might have and answer them in the comments section. But otherwise, thank you so much, guys. We'll see you next week. Make sure to check in with your class's channel to see what the videos are I want you to watch and the work that you need to do. And tell everyone else who wasn't here that they need to be getting on with some work. Thank you very much.